Hi, I'm Thomas Brandt. This is my partner.
I'm Andrew Thompson. So we've got our concept map here for
Lectures 1 through 10.
there you go. So here, let's pop this up so you can see it a little bit better. This is a really janky setup. Apologies.
I'm going to tilt that.
Yeah. Okay. So I think one of the biggest things we focused on since our last concept map, we looked at the deformation. So this is delta. So the deformation, the change in length.
Our Plie equation.
Plie equation. And then that connects to deformation, obviously, and then stress. But also, the gear ratio is going to change this deformation. But more commonly, the gear ratio is going to be used with the angular deformation. So this is the angle of twist, TL over JG, where G is your constant, which is a material property, which is something we could probably add, to our little thing here. So that's just going to be something that's consistent with different types of materials.
And sometimes we can be given a composite material on some questions where you got multiple materials and multiple G's to account for.
Yeah. So I think the biggest key there is just breaking it down. So every time anything changes, either the force applied or the diameter of said material or its hollowness or the material itself, anytime any one of those changes, we're going to have that's when you're going to want to redo your total deformation. So you could also write a sigma in front of both of these equations. So you could have sigma pli and then sigma TL over JG. So that's going to be our method of sectioning. Yeah, thank you, Thomas. But I think that's a big concept there. So just being able to identify where you're splitting up. So anytime you see a change in any one of these, so if the applied forces change, if the what's that J called? What's the
Polar moment of inertia.
There, if your polar moment of inertia changes, so if it goes from hollow, and then this is a constant, so if material changes. But anything you want to add to that?
I actually have polar moment of inertia here too.
Oh, perfect. Yeah.
But
Poisson's ratio, that's a big one.
yeah, that was the newer stuff. So that negative lateral strain over axial strain, which we were talking about, like in a problem. Which one is axial? Which one's
maximum radius?
Oh, yeah. So
lateral?
So lateral is going to be your Y. So
Generally, yes.
yeah. So
like
axial is just where you're applying the force typically. So that's going to be your
240 would be C, right?
value.
Yeah.
And that's used in quite a few equations. That's an important thing to know. We recently talked about bending moment, and on our last homework, there was, for these types of questions, for some of them we had to create our own equations based on a diagram of given like
of an applied force on a beam, you had to create a bending moment diagram and a shear stress diagram.
And a shear stress, that's what I was like, a shear stress diagram.
Yeah.
That was something I struggled with, something I'll definitely study for on the for the test on Friday.
Yeah.
Wow. Wow. That's a big one.
Oh, another type of deformation here is this temperature deformation. So expanding due to temperature change.
Which, connecting that to what we were just talking about with different materials, we were given one problem on the homework where it's like you have a confined walls, or kind of, and then there's a composite material in between, and that material is going to expand at different rates based on even though they're undergoing the same temperature, just based on their material properties.
That is correct.
That's a good question. I could see something like that being on an exam.
So the alpha is another material property here, and then this is your change in temperature, and then just the length. So obviously it's going to expand more for a greater length. And there's a linear relationship there.
Something else that we've been talking a lot about recently is fillets. So whenever you see a fillet question, you're probably going to use stress concentration factor, which we learned earlier, but now we're applying it more.
Yeah, so that's K, and you're going to use those graphs too.
Yeah, there's an important graph you should know. The y-axis is...
The y-axis is your K value.
It's like radius over...
No, I think the y-axis is your K value. The x-axis is big D over little d.
Yeah.
And then depending on which line you're going to use is going to be your R over D or something
Yes,
like that.
that's what I was thinking of. You're right.
So that's your fillet radius.
So I could see that something like that being on an exam, and that's something important. You should be able to read and
Understand.
understand.
Yeah.
Um,
But you can really multiply the stress concentration factor into your, where's that equation? Into this equation here we have your shear stress, or you could multiply it into your plea, right?
Another thing that's been popping, we learned about it in statics, and now we're seeing it more in but distributed load.
Yeah.
How that works on a beam.
And how that's graphed. That's another one with the graphing, the bending moment in the shear stress diagram. Oh yeah, I think that about wraps it up. Anything you would like to add, Thomas?
Last couple things that we didn't have on our last concept map, but a lot of material properties important to understand, and we're starting to get into more things like necking or ductility. We had some question on percent elongation, elasticity, so stuff we learned in Mae120 or 21. It's coming back. You should know how to deal with that.
But all right.
Yeah, that about does it.
Thank you for listening.
Thanks for watching.